Okay, this is the practice test for College Algebra, Chapter 4. In problems 1, 2, and 3, you'll be graphing. For number 1, it would be easy enough just to make a table. And even if you do put it in your calculator, I want you to show me at least 3 exact points off to the side. I'm going to be doing this one by hand, therefore I get to choose whatever I want for the x value. The independent variable, so I'm going to choose a 0, a 1, and a -1, plugging each one of these values in. So the first one I'm going to plug in is 0. Anything to the 0 power is 1. Now you can get these values right from second table. If you want to show me the values like that, you can at least show me that you know how to use the calculator. But you'd have to first press in y is equal to 3 to the x into your calculator. Then you would choose second table, and you could get any of these values that I'm getting by hand. I'm showing you how to get them by hand so that you can practice with your exponents. Okay, the next one, I'm going to plug in a 1. So 3 to the 1 is 3. And then for the third one, I'm doing -1. Anything to a negative power really means that it's a fraction, and the fraction would be written like this: 1 over 3 to the positive power that you're seeing. So this is really, 3 to the -1 is really 1/3. Okay, and then you can just go ahead and plot the points. So 0, 1 is right there, 1, 3 is here, and then -1, 1/3 is approximately right there. Make sure that you know the shape for this graph. It has an asymptote of y equal to 0. That's the x-axis, so this tail flutters alongside of it but doesn't break through it. So this serves as the asymptote holding up that tail, and then it goes off into infinity. Okay, likewise for number 2, I'm going to make a table. I will be demonstrating the calculations by hand, but again, you could enter y is equal to 2/5 to a power of x. You would need to put the base in parentheses in order for this to come out right. If you don't want to use parentheses, then you need to know what this is as an exact decimal, which is 0.4. You could go 0.4 to the x, then you wouldn't need the decimal, the parentheses. In any event, it's pretty easy to do by hand. Again, I'm going to use these real simple values, 0, 1, and -1, and demonstrate the arithmetic or the operations that you're doing. Okay, so anything to the 0 power, whether it's a fraction, integer, negative, anything to the 0 power is 1. Then next one is 2/5 to a power of 1 is just 2/5. Anything to the first degree is itself. So it would be the base. And that's, if you want a decimal for that, that's 0.4. And then the third one, what a negative power actually does is it makes the base flip over. So if you want to just have a generalized approach for how to deal with a negative exponent, this is it. Whatever the base is, flip it over and switch the power to a positive version of what you're seeing right here. And you could have done the same thing to this one. You could have just taken the base, flipped it over, and then changed the power to a power of +1, which is what's right there. Okay, so this is the same thing. You have 5/2, and again, you can turn these into decimals if you'd like. This is equal to 0.4. So you can do that in your calculator by just going numerator divided by denominator, and this is 2.5 or 2.5. Okay, when you go to graph it, it is same shape, Tail's going to flutter along the x-axis, only it's going to go in a different direction. When the base is less than any number less than 1, it ascends to the left, whereas when the base is greater than 1, it ascends to the right. But you'll see that as you plot these points. So 1 2/5, so it's getting very close to the x-axis. And then -1 2.5 starts to climb. So you see that it's climbing this way, ascending to the left. Excuse me. Okay, so that's that graph. This says use the graph of e to the x to obtain the graph of e to the x plus 2. So if you'd like, you can get the points if you'd like using your calculator, which you're going to need it for the calculator anyway, since this base is an irrational number, a decimal that runs on and on. So you can put this into your calculator for y is equal to, and then you can just press second table. Be careful on problems like this, because when it says use one graph to get another one, you need to show both graphs. Okay, so if you do want to get a little table, again, I would concentrate on some real simple values. 0, 1, -1, and then play off those values to get these, and that'll make the work a lot less. Okay, according to what I set up here, any base to a power of 0 is going to be 1, so you can apply that every time you choose 0. That's why 0 is such a nice power to choose. Any base to a power of 1 is that base. And this is approximately 2.7. You can take it further, but there's really no point. And then e to the -1, you can just put that into your calculator. That would just be second. And on the ln key, there is the e to the x. You can press in a -1, and you get approximately 0.4. Now from these values, so this is the original graph, or the parent graph. And then if you want to get the shifted graph, rather than plugging in these numbers and then doing all these operations that are suggested for g of x, what you could just do is try to understand what kind of shifts are going on, because that was a big point of a couple of the sections. What you're seeing right here is a horizontal shift. But horizontal shifts always get switched with respect to the sign. So if this says x plus 2, you're really using -2. Horizontal shift always means that you are performing an operation on the x's. So this is going to be each of the x's minus 2. And I'm talking about off of this original table of values. So each of the x's minus 2, okay, we have 3 x values that we chose over here. So the first one minus 2, -2. The second one minus 2, so that'd be 1 minus 2 is -1. And then the third one minus 2, and you can always put in a calculator if you can't do it in your head. It'd be -1 minus 2. You can do that. Okay, so that now I've already done the x's, the horizontal shifts. Then this positive 3 that you see right here, that is a vertical shift, which means you are going to be performing this operation. No switching here. That's only for horizontal shifts. You're going to be performing this operation on your y's. So you're going to take each of your y's and add 3. Okay, so get on this table again. And let me get this e out of here and just write the decimal equivalent. That'll be a little bit better. I wrote an e there. We can just write what it's equal to approximately instead. Okay, so we're going to be adding 3 to each of the y values. So it's the first y value plus 3, 4. The second y value plus 3, 5.7. So rather than all the calculations you'd be doing if you were to plug in a 0 and then do all of this, and then a 1 and do all of this, a lot less work this way. Okay, again, taking each y, 0.4, and add 3. So this would be 3.4. You'd need your calculator each and every time you got one of these if you were actually plugging it in there. So shifting, much easier. So what you're looking at here is the f of x function. This will give us the f of x function. This shifted table will give us the g of x function. And you're going to put both of them on the graph. Don't forget that on the test, when you're getting one graph from another one, you show both graphs. Okay, so plotting the first table of values, you have 0, 1. You have 1 and 2.7, approximately there. And you have negative 1 and 0.4. So negative 1 and 0.4 really close. So this is the e to the x graph. If you want, you can label each one. Okay, and then this is 3 units higher, so you might want to put the horizontal asymptote in place. Like for instance, for this graph, this is the horizontal asymptote, this x-axis right here. It's called y is equal to 0. Now, if this particular graph that you're graphing is moving 3 units higher, which it is, every single y value is 3 units higher, so this little horizontal asymptote that the graph rests upon, it is also going up 3 units. So you might want to put that in place first, so that when you do start plotting these points, you allow the tail to rest or flutter right above your new horizontal asymptote, which is now at y equal to positive 3. It has risen 3 units up. Okay, now go ahead and plot these points. So negative 2, 4. Okay, so negative 2, 4 is going to be right there. Negative 1, 5.7. It's going to be almost at 6, but at negative 1. So negative 1, 5.7. And then negative 3, 3.4. So just a hair above this line. This horizontal asymptote is called y is equal to 3. So 3.4 would be slightly above it at negative 3. So negative 3, 3.4. So there we go. And there's your tail resting right above the new asymptote that has risen up in the air. Okay, moving to number 4. Okay, in problem number 4, you're finding the accumulated value of $1,200 at 8% compounded quarterly for 2 years. So when it says quarterly, that means your n value is 4. For 2 years, this would be your t value. And then your rate. The rates have to be used as decimals. So the decimal equivalent of 8% is 0.08. And then this would be the principal. Okay, so the work for this one, let me get a piece of paper. Hopefully I have some extra paper here. Have a little more room to work the problem out. Okay, so for problem number 4, I would write the formula down first, just so you can be looking at it as you try to organize your thoughts and the information. Okay, again, these are the bits and pieces of information that are going to be plugged in to the formula. Principal, the amount that's being invested is $1,200. The rate is 8%. You're being paid interest 4 times a year. That's what quarterly means. And you're being paid on this schedule for a total of 2 years. Okay, so A, which means the final amount in the account, will be the following. It's going to result from this calculation. Over N, which is 4, and then it's 4 for N again, times T. Now you might want to clean this up a little bit before entering it in the calculator. Like for instance, you could turn all this into just one number. Just go 0.08 divided by 4 plus 1, which is 1.02 to a power of 8. Now put it in the calculator, because that's not really too much to put in the calculator. So 1,200 times 1.02 up to risen to a power of 8. And you get $1,405.99. Okay, that's number 4. Number 5. Let's see, I don't know if I have enough room to work this out. Okay, so now you are writing the equation in exponential form. So when you write this in exponential form, that means that you are getting rid of the word log. The way you do this is by using the definition that takes you from log form to exponential form. Basically, you use the base on the log, and it becomes the base of the exponential expression. So you're going to push it up. Okay, it's still going to be the base, but now it'll be the base of an exponential expression. Keep that equal sign. Put the equal sign so that you have a left and a right. And now you're going to switch the remaining 2 items. We've already dealt with this. We've done something to the 5 by pushing it up. Now we're going to act on the 2 remaining items, because the log is not even part of the answer. When you go to exponential form, there is no log in your answer. So therefore, we only need to deal with the x and the 3. And the way you deal with them is they switch sides. This 3 comes over to the left side of the equal sign. Here it is now. On the left side, acting as the power, and the x takes its place. So there you go. You now have that in exponential form. Okay, you can leave it just like that with a base and an exponent, and then x is equal to. When you go into log form, now you're going to make the word log appear. Okay, so now what you have to do is remember that this base will also be the base in log form. So what you can do is put the word log where the base and the power is, but then drop that base down towards the bottom of the G. Put the equal sign there so that you establish a left and a right side. And what you're going to do is switch the remaining 2 items. We've already placed the 4 with the log, so we just have to deal with the -2 and the 1/16. Let me move over this equal sign to give myself a little bit more room. But you need that equal sign so you can establish clearly the left side from the right side. So the 1/16 is on the right side presently. Now it's going to be on the left. It'll now be the new argument of this log, and then the -2 comes over and takes its place. Okay, and that's the answer. You can put this in parentheses if you'd like, or not. So it'd be the log of 1/16, base 4, is equal to -2. Okay, evaluate the expression without using a calculator. So when it says no calculator, no decimals. Do not press it in your calculator. Okay, so the first one, what you're going to do is, again, this is all going to be about you knowing how to rewrite from log form to exponential form as I did in number 5. So right now you're going to say that this is equal to some unknown value. And now we're going to rewrite. When you rewrite from a log to an exponential form, you just take this and push it up. It becomes the base. Put your equal sign. Okay, so these things are on, I'm working on the left side right now. You push that up, it becomes the base. Bring the x over to be on the same side. In other words, over to the left side. Let the 16 take its place. Now look at what you have here and ask yourself what value needs to be right here in place of x for this statement to be true. It would have to be a 2. 4 squared is 16. Therefore, x is equal to 2. And that's the solution. That's what it evaluates to. This expression, although you could not have calculated it while it was in log form, you can calculate it once you put it in this form. So this expression right here is equal to 2. Okay, same thing here. This is equal to some unknown value, and you're just going to take this log expression, rewrite it in exponential form. So you're going to go this, push it up, let it be the base of your exponent, put your equal sign. Now let the x come over here, but you always put it in the power position, and then let this square root of 9 come right over here. Okay, let's keep working with what we have. Over here we have, I'm going to just move it over here a little bit so I can continue working. So we have 9 to the x on the left-hand side, and on the right-hand side, if you recall what I went over in class, that when you want to go from radical form into power form, like this is written with a base and a power, a base and an exponent, let's write this side like this as well, the right-hand side. So any radical can be written as the base or the radicand that you see underneath the radical, that's the 9. Use the power that it has underneath the radical as the numerator. And then this square root, you use the index as the bottom. So what does this have to be for these two sides to be equal? X has to be 1/2. And what that means is that all of this log of square root of 9, base 9, is equal to 1/2. You can also get that answer by the inverse property. Okay, last one. I don't think I really have enough room, so I'll move to this paper. It's log of 1 base 12. This is number 9. Log of 1 base 12. Currently that is equal to some unknown value. I'm going to rewrite it, pushing this base up, but still acting as a base, dropping that equal sign, and then switching the two remaining sides. Okay, again, you see that I'm using this definition over and over again. This is the 4th or 5th problem where you're going from log form to non-log form. This still acts as a base. Here it's the base of a log. Here it's going to be the base of an exponential expression. So the x comes over, playing the role of the exponent, and the 1 goes over to take its place. Okay, the only way that anything to a power can be 1 is if the power is 0. It's the only power that will work there. Therefore, log of 1 base 12, although you could not evaluate it in its original form, now you know that this whole expression is equal to 0. Whatever you get for x is what that evaluates to be. Okay, next problem, number 10. Number 10, use the graph of log of x base 5 to obtain the graph of log of x minus 2. Okay, so what we can do here is we can make a little XY table. So right now you can go y is equal to log of x base 5. Okay, this can be your original graph. This will be the shifted graph. Okay, so now what you could do if you want to work with this is that you can rewrite this in non-log form. So if you want to get this in exponential form, you push that up, still a base, you let the y be the power, and this x come over and jump in its place. Okay, same thing that I did in the in numbers 9, 8, 7, and then I also did it in number 5. You're going from log form to exponential form. This just gets pushed up like this. What's by itself over here comes over and becomes its exponent, and that x goes over and takes its place to be the term standing by itself. Now make a table. But now look at where the y is. You would have to, I know you're used to picking values for x, but once you rewrite this, these two switch roles, so you're now going to have to choose values for y to begin with. Okay, so the values for y here, again, the simple ones are 0, 1, and -1. And when you put a 0 right here, you get a 1. It's 1 point you're going to be plotting. And when you put a 1 there, when you use this right here, you'll get a 5. And when you put a -1 there, you take this base, let's practice what we did in a couple of other problems, flip it over, in other words, the reciprocal, and the power that it is attached to it is now the opposite in sign of this, so just 1/5. Okay, we can plot that, and you can make a table for the other one as well. So this would be 1, 0. You're going to 1, 0. That's right there. 5, 1 is right here, and then -1. -1 and 1/5. Oops. Make this a little bit better. Okay, then let's do this graph here. Again, you can rewrite this. This right now you're looking at y for the shifted graph. Y is equal to log of 5 x minus 2. And so if you want to rewrite this, it would be take this base and push it up. It's still going to be the base, but this y is going to come over to the right, acting as the power, while this, what was over here with the log, will come over and take its place, which is x minus 2. So now the calculation that you're going to do here is 5 to the y. And I think I would get the x all by itself, so that once you do the calculation, you have the x all by itself. So if you bring this -2 over here, it's +2. Okay, so you can plug in 0, 1, and -1, which you've already done on the other table. The only thing that's going to be happening is that each one of the y values, you're going to be adding 2 to it to get to the x value. Okay, so let's... Okay, so the y values we're going to be using again are 0, 1, and -1. Now you already know what happens when you plug in a 0. You get a 1, and now you're going to add 2, you get a 3. Then you have already plugged in the 1 right there. You got a 5. 5 plus 2, 7. Then you're going to plug in a -1, which gives you a 1/5, because we did that value over here, plus 2 is 2 and 1/5. So 2 and 1/5 is going to be the power that you get right here. 1/5 is equal to 0.2. Okay, so now you have all three values on the shifted graph as well, and you can go ahead and plot those. So it's 3, 0 right there, 7, 1, and 2.2 and -1. 2.2, -1. Okay, moving to number 11. In problem number 11, we're doing the log of 1/100. Move this to where you can see it. And you're going to evaluate it without a calculator. So this is equal to some unknown value, and I think what you should do is you should try to rewrite the left-hand side, and you'll see that you'll be able to use the inverse property. First of all, this 1/100 is the same thing as 1/10 squared, and that 10 squared represents the 100. Since it's happening in the denominator, this entire argument can be written as 10 to the -2. Okay, so all of this is what was in parentheses. Drop down the word log. Understand that when there is no base written on log, the base is said to be a 10. And so you can already begin to see the value of what's on the left-hand side. This would be a direct application of the inverse property, that when this matches this, when the base matches the argument, then the power is what this is equivalent to. That's the inverse property that we learned. Okay, so that takes that out, takes the word log with it, equal to -2. Okay, number 12. Okay, problem number 12, you have 10 to a log of 5th root of x. Okay, now this is just actually a variation of the inverse property. I'm going to rewrite it for you, showing you some of the things that maybe you're not seeing as you look at the problem originally. The log that you see here is also base 10 because there's no base written there. And this can be written in power form as x to the 1/5. Okay, so this is just a more advanced application of the inverse property. If this base matches this base, then they take the word log with it, and this is equal to x to the 1/5. Okay, that takes us up to 12, and then let's finish with number 13. Okay, here you want to know what this is equal to. And you can set it equal to x, or you can just look at what they're giving you right now. You can say it's equal to some unknown value, or you can just simplify it the way it is without putting equal to x. So anytime you see ln and they don't write the base is said to be an e. This right here, the expression that you're seeing right here, is e to the 7th, but to a negative power. Okay, and that's because the e to the 7th is happening in the denominator. Okay, now what you see here is an application of the inverse property. When this base matches this base, it takes the log with it, resulting in a value that's equal to whatever is in the power position. So this whole thing, and you could call it x if you want to, it's just the unknown, the name I gave to the unknown, is equal to -7. Okay, that completes all the way up through 13.